Okay, so in the previous videos, we've talked about scalar multiplication and vector addition. And so let's see one application of these operations. So let's say I'm working in R2 and I have this vector minus 4, 5, and that I've drawn over here with this directed arrow. So I've gone 4 units to the left, 5 units down. And what this question is asking is, okay, can I find scalar x1 and scalar x2 so that when I take x1 times the vector 1, 0 and add to it x2 times the vector 0, 1, it's going to give me back minus 4, 5. So here we're dealing with a sum. So this means we're going to set up a parallelogram. We don't know how long the sides are going to be, but I know that one parallelogram, or at least one side of the parallelogram, is going to go directly to the right or the left, right? It's going to point in the horizontal direction. And the other vector is going to tell me how far up or down we go. So what you can imagine is this is like a grid for the streets in a city. And you want to get to this location over here. And you are standing at the origin over here. So you stop and you ask somebody, hey, how do I get over to minus 4, 5? And you're in this grid city. So what they're going to tell you is, well, you're going to want to go 4 units to the left. So you're going to walk 4 blocks to the left. So that's a minus 4. And then you're going to head 5 blocks directly down. So you're going to go minus 4 units to the left, and you're going to go minus 5 units down. So that's what we've drawn over here on the right. And so notice now I've expressed this vector minus 4, minus 5 as the diagonal of a parallelogram, which is spanned by 2 vectors, one of which has direction which is at least parallel to 1, 0, and the other is parallel to 0, 1. And maybe you're just thinking more along the lines of, well, if I have minus 4, 0, and I add to it 0, minus 5, well, that's going to give me the vector minus 4, minus 5. So one way that you can think about this question again is it's saying, okay, if you want to wind up at minus 4, minus 5, give somebody directions about how to get there if they only can move directly to the left or to the right and directly up and down. So if they lived in a city that had perfectly, rectangular gridded streets. And this is typically how our minds are most naturally wired to work, that is, giving directions that are directly to the east and west or north and south. So for that reason, we describe these 2 vectors in R2 as standard column vectors. So we would denote E1 as a vector whose first entry is 1, second entry is 0. E2 denotes a column vector whose first entry is 0, but second entry is equal to 1. And again, these are probably the nicest type of vectors to work with because this just divides up R2 into a very rectangular grid. Okay, so now let's take a look at a similar question, namely, how can I multiply and add vectors so that in the end I wind up with this vector minus 4, minus 5. So we want to wind up at this location in the plane in R2, which is 4 units to the left of the origin, 5 units down from the origin. But now we're no longer thinking about our kind of more natural directions of going straight to the right, left, straight up and down, but rather we have 2 different directions. So now you can think about this city, which is still set up in a grid, but it's a diagonal grid. And so some of the streets move in a direction which is parallel to the vector 2, 1. So that I've drawn in red over here. So all of these vectors that have that are going up and to the right, these are all parallel to 2, 1. So I'm going to think about all of my blocks either move parallel to this direction, or we can move parallel to the direction of minus 1, 1, which is this vector that I drew in blue. So I have some streets that are parallel to the blue vector, and my other streets are parallel to the red vector. And I want to think about how can I move some distance in this direction, some distance in that direction, and wind up at minus 4, minus 5. So one way to wind up at -4, -5 would be, let me first move along this block. I'm going to go all the way out to here, and then I'm going to travel in a direction which is parallel to the vector -1, 1. And by adding these two vectors, I'm going to wind up at the same endpoint at -4, -5. So now this green vector is the diagonal of a parallelogram which is spanned by these two vectors. So then I can calculate, well, how many times how far did I need to walk in this direction along 2, 1? And so this direction over here, I've gone, this is the vector 2, 1, this is the vector 2, 1 again, and this is the vector 2, 1 again. So altogether, we've gone 3 vectors worth of in the direction 2, 1. And then in the other direction, we've gone 2 vectors of length -1, 1. So I'm going 2 directions over here. But what we also want to be mindful of is if we're going in the opposite or the same direction as the vector. So 2, 1 points up and to the right. But however, in order to wind up at -4, -5, we need to go down and to the left. So this is actually scaling and changing the direction. And the same goes for this vector in blue. The vector -1, 1 goes to the left and up. But we need to walk along this direction to the right and down. So that would be -2 over here. So what I can see, and we can check this, is that if I go -3 times 2, 1, and then I go -2 times -1, 1, that doing the arithmetic gives me -4 and a -5. So that checks out. And you can double check your vector arithmetic to make sure that this gives us the right result. So on the previous slide, we answered this question looking at this geometrically, kind of thinking about it. If you lived in this diagonal world, how could you give directions to somebody to wind up at this terminal point? But let's say we don't have the picture in front of us. So how could we solve this problem algebraically? Well, this looks a lot like a linear system of equations. So maybe let's try and imagine this as a linear system. So doing the arithmetic here, this right side of the equation would be 2x1 minus x2, and that should equal to -4. So that's where this first equation comes from. And then I have x1 plus x2, and I want that to equal -5. So finding these constants x1 and x2 are equivalent to solving this system of 2 linear equations. And so how have we been working on solving these systems? Well, we would set up augmented matrix. So we have our coefficients here, and we have our constants over here. And then we apply the Gaussian elimination, row reduction, to express this matrix in its reduced row echelon form. So I skipped those steps, but this would be good practice for you to try and do some elementary row operations to verify that it can be written in this form. And once we've got it in this form, we now can see that x2 should equal -2, x1 is going to equal -3. And this is totally consistent with the picture that we had on the previous slide. So if I want to wind up at -4, -5, I can go in this direction 2, 1, -3 times, and then I can go in the direction -1, 1, -2 times, and that's going to put me at the same endpoint over here. So there's another way to see why x1 is equal to -3 and x2 is equal to -2. And let's see how this would work for another vector. So let's consider some other vector w, which is this elementary column matrix, column vector 1, 0. So that would be located right here. We could ask a similar question: are there values x1 and x2 so that when I take this sum, I wind up with 1, 0? And although x1 and x2 might not be perfectly nice integers, yes, we can do this. And so I can do this in a similar way of thinking, well, let me move a little bit in this direction along that line, and then let me move in a direction which is parallel to the other one. And what happens is that these values for x1 and x2, they can be fractions, they can be irrational numbers, they can be anything. As long as there are some real numbers, x1 and x2, that I can multiply each of these two vectors by and add together to wind up with this vector w, that's fine. So we can wind up anywhere in R2 by going some combination of these two vectors. So any vector w that lives in R2, we can decompose into some scalar times the vector 2, 1, plus some scalar times the vector -1, 1. And these scalars don't need to be integers. That's the point I'm trying to make here.